Right. So many thanks everyone for attending this this masterclass. I would like to just address 3 points on this masterclass. It's going to be the intention for me is not to dive deeply into each topics because they are very vast. Sensing, we had a glimpse of sensing this morning thanks to Afrim. We talk about. I will talk about technology. I will talk about also service enablements on your networks. But those are very big topics. So I'm just planting seeds in this presentation during those 45 minutes. And I would welcome, or I expect you to contact us for further discussions if you are interested in any of those 3 topics. So without further ado, I would like to first talk about the digital signal processing. So Sienna mentioned and introduced this topic this morning. There are hundreds and thousands of white papers, conferences, maybe not 1,000 conferences, but there are many, many publications on this topic, why DSP has been a key innovator in subsea transmission over the past few years, how we went from a basic 10 gig per channel to now 800, 1.2, in the future 1.6. So extraordinary achievements have been done on this field. And today I'm kind of proud to introduce to you to a new evolution of the DSP at Nokia with our latest DSP, the Photonic Service Engine 6, that is going to be released at the end of the year. And I will talk about some field experiments that we are doing with the cards as we speak. The first innovation, the first topic I would like to cover is the scale. So with PSE-6 now, what you are able to achieve is 1.2 terabit per carrier. So that 1.2 terabit per carrier has been demonstrated on the network in Spain, and I will show you the press release with that. What it's also able to do is so you have the module itself, the DSP. The DSP is integrated into a module which is a multi-chip module, and that multi-chip module is built onto a card. That card will integrate 2 modules, therefore one single card will generate up to 2.4 terabit per second. So it's one of the highest density optical transponder on the market. The other thing that the PSE-6, the Photonic Service Engine 6, is going to achieve for you is to increase the reach. So at 800 gig, we are able to go 3 times further than the previous chipset generations based on 7 nanometer. So this is obviously a huge achievements in terms of performance. The other achievement in terms of performance is related to sustainability. So sustainability is a big buzzword that everyone uses. Not sure it's working properly. Everyone is talking about it. We had these panel sessions, which was very enlightening this morning. Everything will contribute to sustainability, but in the telecom era, one of the things which will contribute is obviously the higher baud rate and the possibility to effectively decrease the amount of hardware you're going to need. So with the PSE-6, we are able to decrease the power consumption of the chipset itself by 40%. And if you consider that that card by itself doesn't, the chipset by itself doesn't fit into as a standalone element, it's part of a bigger module, it's part of a common equipment, then it's going to decrease the power consumption by 60%. So one thing which is interesting with this technology is that not only it is backward compatible with the previous generations, you don't need to throw away all your common equipment, all your existing network to benefit from that new technology that we are introducing today. So this is a bit of a sales pitch that I've made so far. Let's see what it really can achieve. So I will start with this first a publication that was made a few months ago. It's a lab experiment, so it's not a real deployment. It is a lab experiment, and it is being achieved in between Nokia Bell Labs and our friends of ASNs, our colleagues of ASNs. So in the lab, we've achieved the transmission of an 800 gig waves over 7,865 kilometers. So it is, again, on a recirculation loop in the lab. It's not a real product per se, but this is what we've been kind of, that's the goal that we've been setting for our product. The second record that we've achieved is 41 terabit. It was done by ASN on an unrepeated link, which was 291 kilometers. So again, thanks to this 5 nanometer CMOS technology, we are able to increase the baud rate, go further, and increase also the capacity per channels. But as you can rightly say, this is this is a lab experiment. So what can we really do in the field? So we had 2 press releases, one with Lintia, the other one with Colt. Today I'm going to talk about the Lintia one, just for the interest of time. During this trial, we've achieved 2 things. The first thing was an experiment in Barcelona on the metro network, where we transmitted successfully 1.2 terabit per carrier. So again, it's one of the highest bit rate in the industry today. It was achieved through 5 reconfigurable OADM. So we had it was done on a real network that was already in place, and the card was simply slotted onto an existing common equipment. The other part that we've achieved is we scale down from 1.2 to 800 gig, and we have achieved a transmission of 1,900 kilometers on a link between Barcelona and Lisbon. So it was a 25 span link with 10 reconfigurable ROADMs. And the reason why I'm mentioning ROADMs is that every time you go through a ROADM, you have penalties. So with the real card, we are going through a real network with real penalties. So some of you are maybe a little bit worried because we are in a submarine topic, in the submarine masterclass, and so far the global warming hasn't been such that Barcelona and Lisbon are surrounded by waters. They're not islands. It is definitely a terrestrial implementation, a terrestrial field trial. But as we speak, we are running since yesterday error-free with our latest generation of card on a transatlantic system, and there will be a press announcement hopefully soon showing you an 800 gig waves on a 6,600 kilometer system across the Atlantic from a tier 1, big tier 1 in Europe. So stay tuned in this field, but the card is real, it's working, it's performing extremely well. So this is the first topic on the DSP innovation. I don't know if we want to keep the questions at the very end, but I'm going to move to sensing. So if we have questions right now, we can take some questions. Otherwise, we can wait for the end. I don't know if. Okay, so the next topic I would like to talk about.
I have a question. Sorry. Can you go back to the previous slides on the lab test? The one previous to this year. Right. So was this done on the ASN testbed itself?
Yes.
So you have the option to do both a recirculating loop as well as a straight line, right?
Yes.
So would this have changed if it was on a straight line versus recirculating, the 7865 kilometers?
So if the deployed testbed is matching exactly the recirculation loop parameters, no.
Okay.
But there is more. There is obviously on a recirculation loop more penalties than a straight line. So it's really the worst case scenario.
Okay. The other one also is now you have done 41 terabits over 291 kilometers, right? So what was how many channels was that? It was 30.
So I fear that you would ask me that question because I told you the answer.
Oh.
But it was done on the C-band only.
Okay.
it's a mix of different bit rates, basically. So you can't have through the C-band window all the everything at 800 gigabits. Some of them are a little bit lower, which makes the 41 terabit.
Do you remember what the spectrum available was when you say C-band? Was it 4.5?
Yeah, it was the basic C-band.
Okay.
So 4.5 terahertz is not the extended C-band.
Okay. And this was full fill, right?
Yes.
It is not like you put a line rate and then assume
no.
Okay.
Yeah.
All right. Okay. Thanks.
And actually, you mentioning a good point. That chipset that I mentioned, the 5 nanometer chipset that I mentioned, the PSE6, is being integrated on the ASN transponders and the Nokia transponders. So in the previous generation, it was also the case for the previous generations, but again, we're working with ASN on those developments. Okay, so sensing is going to be relatively quick, and thanks to Ephraim, he has done most of my job already, so I don't have to do it again. Sensing is a very vast topic, so it's difficult to capture everything. We mentioned this morning mostly the tsunami applications, but sensing can cover, it's not dedicated to subsea only, it's also covering terrestrial. So in terrestrial, you can have also some sensing applications, and I will show you a little demo that will illustrate that. You can, for instance, if I mention terrestrial or subsea, you can detect some patterns that will help you identifying a potential problems and take preemptive actions to make sure you reroute important traffic before an actual cut happens on the network. So this is one application among many, many other applications. But let's focus again on subsea. So when it comes to subsea, the key sensing applications are listed here. Afri mentions the detections of threats on the wet plant, threats on human beings. There is also one important point, and again, I'm repeating what Afrim said, the need to detect and locate geophysical phenomena. So the location is the tricky part. Other sensing technologies are being applied to actually worked with other United Nations organizations on mainly the ocean decade, in which Nokia and ASN are participating to help monitoring some aspects of the climate change. So, for instance, water pressure, which indicates a rise of sea level. We can also monitor some mammals migrations so that we can monitor populations and detect, paths of migrations. If those paths are changing due to the global warming, we can also do a lot of monitoring related to those climate change applications. So ASN, Nokia Bell Labs, and also Nokia Optical Network divisions have developed jointly several techniques. I will talk about 4 techniques. And again, one of those techniques were mentioned this morning by Afrim. Typically, you got 2 sensing applications or 2 techniques. One technique is by using dedicated sensors. That's kind of obvious. I will present the OptoDAS and the smart applications that Afrim presented. The other technique is to reuse coherent receivers and to use the streaming telemetry coming from those receivers to monitor various aspects of the transmission. The first application that I would like to mention is this OptoDAS. Again, this is a development from ASN. This has been deployed and successfully tested on many cables. There are lots of field trials. And as you can see, to confirm what Afrim was saying this morning, the reach is mostly for up to 160 kilometers. So it's a little bit longer than 100, but it's range, and it's mostly dedicated for oil and gas, shore ends, and relatively short distance up to the first subsea repeater. The other technology that is available, that will be available, sorry, in 2025 is the results of the collaborations between the collaboration between Nokia and ASN as part of the United Nations Ocean Decades. And this is effectively this C node, which is made with dedicated sensors. Again, the key applications for those modules is to be detecting earthquake, to detect tsunami waves, prevent populations about tsunami warnings. It's also a scientific surveillance with sea bottom movement, sea level rise, and also it monitors the drift of the seabed. So the first deployments are planned for 2025. Contracts are being signed. This is being integrated in some cables that will be laid starting in 2025. So the other technique that I was mentioning is related to using some existing coherent transponders. And typically, a coherent transponders is going to generate a coherent light channel, coherent light channels that will be transmitted across a wet plant. So obviously, gradually, the signal will be severely distorted because of various phenomena within the transmission, chromatic dispersion, polarization mixing, phase rotation, etc., etc., etc. And at the very end of the transmission, you have all the DSP technology applied to, for instance, compensate for the accumulated chromatic dispersion, to correct errors with a forward error correction, etc., etc. So this is the basic transmission. But what is also possible is, or what is also happening is that some punctual events are triggering some impairments in the transmission. And those impairments can be, trains on tracks causing some vibration and disturbing the polarization. It could be winds in the case of terrestrial network on aerial fibers. There are many, many reasons for impairments to degrade the transmission. And again, we can use all the streaming telemetry that is being generated by the DSPs to do actually three things. So one of the things that Nokia has been offering since the previous generation of DSP is typically to web scalers. They use that streaming telemetry, they process that streaming telemetry through machine learning, to artificial intelligence. And what it does is basically, it's going to detect patterns in the disturbances. And by correlating, that's why I'm mentioning machine learning, is by correlating all those events, those disturbances, they will associate an event and make preemptive actions related to that. So that's the first option. The second option that Nokia is developing with ASN is a package that can be added to our existing NMS ecosystem, and it's called Health and Analytics. Again, it's going to be based on machine learning. If you don't have the time or the ability to do it yourself, you can use that package, which is available early next year, to effectively exactly do the same thing, detect patterns in the disturbances on your system and on the transmission. The last thing, which is a little bit more in the future, depending on how sensing becomes an important factor in the industry, is going to be to integrate some of the processing, instead of doing it at the software level, to do it at the hardware level directly within the DSP. So here I've got a little demo, which is animated. You can see that a robot, which is at the bottom end, is interacting with a fiber that is going to link two transponders which are operating error-free. At the other end of the slide, you can see a little animations, and you can see that every time the robotic arm is doing something, you've got, sorry? Oh, sorry. So every time you can see some disturbances, those are the perturbation caused by the robot. So what is actually happening is that the DSP is going to retrieve the polarization in this particular case, and it's going to analyze that polarization through three parameters, which are the Stokes vectors that Afrin was mentioning this morning. And one representation is to have this linear. The other representation is to have a sphere. I don't know if you're familiar with that, but it's another representation. And every time the robotic arm does something, you could see the perturbation happening. And what is key is to be able to detect each specific movements to define what is the movement created by the robots. So you can extrapolate that to real case network with, on a either subsea or terrestrial, where you effectively can correlate what you observe on the Stokes vectors with the actual fault about to happen. The third technology, as again was discussed this morning, the study of the Stokes vectors. As you can see, this is the perturbations or the impairments that you observe at the end of the transmission is the result of all the integration through the system. So it's very challenging to actually detect exactly, something is happening. You can detect on a span that something is going to happen, but you don't know exactly where on the span this is going to happen. So it requires a more advanced analysis, and the Stokes vectors are not just enough to achieve that. So here, it's a product that we are working on and developing internally. So it is, still a little bit a work in progress, but effectively by using the high loss loopback, the actual connection from the transmit and the receive within each repeaters, and by correlating the phase and the polarizations, you're able to much better predict where the impairment is going to happen. And it can work on any system which is implemented with high loss loopback, which I believe is 99.99% of the subsea systems, because the high loss loopback is something that is used anyway for COTDR. And if you're familiar with COTDR measurements, this is something that is delivered as part of any subsea system. So we're reusing any wet plants with high loss loopback to carry a much finer analysis of the locations of the faults. So this is our first. So here I'm showing an experiment that we've done onto a system across the Atlantic, and as an example, I'm showing the swell events that we would be able to detect with this technology. So at the very end of this, I'm just summarizing the 4 options that we have developed or about to develop between Nokia and ASN. So I'm just going to skip through that quickly. Again, is there any question on the sensing? It was very quick, but again, Afrim did an excellent job this morning already to cover some of the topics. So before moving to the final part. Nope. So far we talked about DSP, which is, hardware. We talked about cards, performances of the cards, again, hardware. We talked about sensing, still hardware with a bit of software involved. I'm going to move on to more software applications that is available, that has been developed and implemented in several networks around the world. One is in the Middle East already using this application. Another one is being used by a tier 1 customers in Europe. And what this is what we call service enablement. So it's an innovation in the field of network management. And the way we can summarize this service enablement platform software, or it's to effectively say that it sits on the top of your existing NMS. So you have your existing NMS, classical NMS, planning, provisioning, monitoring, and alarm reports, and it sits on the top. So the main purpose of the service enabler, Wave Suite Service Enabler, is to help customer virtualize their network and their optical network, and to use it to create innovative services, to attract more customers, to create business models which are different than what you would do traditionally with your own network. So what you're able to do is to use, obviously you have an existing network, which is yours, but you can partner with other players, other people owning their own optical networks, amalgamate that into a virtual network that you can use at your own and propose that service to your own customers. Therefore, you can go further than your existing networks as it is today. And again, that platform sits on the top of your NMS. It's an open platform. So on the paper, it doesn't necessarily matter whether it's a Nokia network or another network. So what I'm showing in this relatively complicated slide is actually a typical network configuration. So you got your optical network, that's your physical assets. You've got the network provisioning, management, and control, that's your NMS. Depending on who who is the supplier of the network, you have different additional software add-on. In the case of Nokia, we have an add-on for planning, for network planning, that sits on the top of the NMS. So you can create a virtual representation of what you want to do and apply it through the NMS on the network. You got a network analysis and optimization. So again, this is the possibility to take a picture of your network and see whether it's configured properly, whether it could be optimized. And if it can, then you can, through that package, send some commands through the NMS to optimize your network. Diagnostics, enablers, synchronizations, trendings, etc. All those Nokia specific add-ons sits on the top of the Nokia NMS, and all this forms the Wave Suite ecosystem. The Wave Suite Service Enabler sits on the top of that, as it is represented in green on the picture. So what you can do with this Service Enabler is you have three primary use cases, which are quite different and helping you to differentiate from your competitors. The first use case is kind of tentatively represented here with, at the very bottom, your physical network. Then the green boxes are theoretically representing you and your partners tapping into the same physical networks. And you virtualize the representation of the physical network. So one green box would not necessarily see what the other green box or green sphere is representing. It just creates a virtualization or a tenant slicing on your network, and that is going to be what you are going to sell to your customers. So you can imagine that this physical network can encompass someone else's network, obviously providing that you have this agreement with them. So everyone will have a Wave Suite service enabler, and those two pieces of software will talk to each other to create that virtualization. And then on the top of that, you have your customers. So that's the traditional model. With the Wave Suite service enabler, what you can also do is tap directly into the physical network if you want. So you don't necessarily need to intervene into virtualizing your network. Once you've done that, the other use case is to offer to your customer bandwidth on demand. So your customer, through a graphic user interface, will be able to provision a service, and that service will then be orchestrated through the different layers of NMS that I was representing before to commission the service. But what you get through this bandwidth on demand use case, that your customer is now going to be able to have access to SLA. It's now going to be able to access to information about latency. It's now going to be able to access so I mentioned SLA, latency, and quality of service. So all those things would mean that now you're not just having a service, your customers are going to be able to access to, at least today, to 3 KPI or 3 indexes to monitor the quality of their services. One of which I forgot to mention is also the actual usability of their service, so they can monitor how much bandwidth is being used. Therefore, you can decide on a global network which are the paths you need to increase, upgrade, which are the ones that are less relevant. So in a nutshell, without entering into too many details, this is what the service enabler is doing today for some customers, which are taking benefit of that platform. Those customers are already using it on their own network. They are discussing among themselves about how to merge their 2 platforms or 2 networks into one big ubiquitous network to create, more reach, more services. Now, Islam is here. We have a little demo. If you want to dive deeper into the graphic user interface, exactly what you will see, how you're going to use that service, please feel free to discuss the details with us. And I wanted, but I was told it was perhaps not really the best place yet to show some of those real implementations that we have in Europe with a tier 1 customer. Again, one in the Middle East with a customer who is actually one of the most innovative use of that platform is to effectively remove completely their own kind of NOC intervention. Their customers are capable to provision services on their network directly without the need of intermediate level. So again, it's going to improve the time to service, the time to revenue, et cetera, et cetera. So with that, I think that's the end of my presentation. I thought I would be running out of time, but I'm 12 minutes ahead of schedule. So maybe we can have more questions, more popcorns and ice creams. Anyway, if you've got any questions, now is the time. No questions.
Benoit,
that's me.
Are you able to comment on the cold network trial? How long was the link? In your first.
So the cold trial was on a link which was from Madrid to Lisbon.
Okay.
So it's a shorter link. It was done with 800 gig. Difference was that compared to the Lintia trial, it was done with a 22 span. So it's shorter spans with more ROADMs involved. So with the Lintia, it was 10. With Colt, it was, I think from memory, 15. Okay. So it's still 800 gig in both cases. One route is shorter than the other, but you got more filtering penalties.
Yeah. And fiber type in both cases, G652 or G655?
So those are G652, yes.
Okay. Thanks, Bernard.
So again, I do apologize because in 45 minutes, I thought I wouldn't have the time to cover everything, but really, there are a lot of notions, stuff we do. We got hundreds of people behind every developments, every, applications I'm referring to. Feel free to contact us. Again, the best thing to do is if you give us the opportunity to do a field trial, we would be happy to effectively demonstrate sensing, demonstrate capacity, demonstrate PSE6, and show you that obviously Nokia is not just a mobile phone company. We're actually not really a mobile phone company. We still make mobile phones, by the way, but Okay, well, thank you very much for your time. And I give you back 9 minutes of your time.